Okay. So let's continue. Today we're going to be talking about closed sets. I left some of the stuff we had from last time up here since we don't have to worry about school kids erasing the board. So, but all we'll care about is going over what exactly a topology is and what exactly an open set is. We're done caring about basis for this section. It'll come up again. So back to what a topology is. So when we talk about a topology tau on X, what is that? It's a collection of subset of X. It's a collection of subsets of X satisfying these three properties. First property, that whatever that collection of subsets is, the empty set has to be in there and the entire set X has to be in there. Second, we require that anytime you have a finite number of sets in tau, any finite collection of sets in tau, their intersection is also in there. And then the third condition is any arbitrary collection of sets in tau, for any arbitrary collection of sets you take from tau, their union has to be in tau. Now remember, what do we call the elements of tau? No. Basis elements is for, when we're talking about basis, we call them open sets. The elements in tau, those sets in there, remember tau is a collection of subsets of X. Everything in tau are sets, right? Tau is a collection of subsets of X satisfying these three properties. So everything in tau are sets. We call the sets in tau open sets. If I say U is an open set, you know that U is a subset of X that is contained in this collection of subsets. Right?
Okay.
Okay. So that's what an open set is. Section 1.3, we're now going to be talking about closed sets. Now, keep in mind, these are just names. Just because a set is open doesn't mean it can't be closed. Just because it's closed doesn't mean it can't be open. They're not opposites. Having one property doesn't mean you can't have the other. They're just names. And we'll show exactly how they're related here. But just because a set is closed does not mean it's not open. It's not like a door. Okay. So before we talk about closed sets, let's go back to definition that we've already talked about once, but remind us of it, make sure we understand it. Let U be any subset of X, then A equal to X minus U. A is everything in X that's not in U. A is X minus U. We call A, which is equal to X minus U, is the complement of U in X. It's everything in X that's not in U. And we denote it by U to the C. Now you might have seen this notation, U with a line above it for set complement before. We won't be using that in this class because this is going to be special notation that we'll see next week. So we can't use that. So the notation that we use for complement is this power script of C. Good so far?
Okay.
You understand what the complement of a set is? So if I've got,
So should the union
here's
of
X, here's U. The complement of U is everything outside of there that's also in X.
so the union of them should create X, right?
Yes. U union, U complement is always equal to X, and U intersect U complement is always equal to the empty set.
Okay.
Make sense? And the complement only makes sense when you have this X already defined. Remember, A is the complement of U in X. Now, from here on out, since we're talking about topological spaces, we're going to drop the in X and just talk about complements. And it's assumed that when I talk about the complement of A, I mean X minus A, where X is a set that I'm using for my topological space. Make sense?
Okay.
So this is going to be true in the context that we always talk about complement, because we're always going to be talking about it with respect to some overall set X. Sometimes we call this the universe that we're in. Okay. So that's what we mean by complement. The complement of U is just X minus U. Okay, so now we're ready for the definition of a closed set. So a subset A of a topological space X, so A is a subset of X, X is a topological space, so it has some associated topology, tau, that we're not bothering to write here. So a subset A of a topological space X is closed, provided that X minus A, or the complement of A, is open. So a set is closed if its complement is open. Make sense?
But that set could also be an open set, right?
So A closed implies A complement is open, is in tau. This set might also be open. We didn't say anything about whether or not A was open. All we know is that if A is closed, its complement is open. And that's an if and only if. If A complement is open, A is closed. If A is closed, A complement is open. That's the definition. So a set is closed if its complement is open. So let's look at some closed sets real quick on the standard topology on R. You remember what the standard topology on R is?
It's the union of the open intervals.
Yes, any open interval or union of open intervals or the empty set. If it's one of those three things, then it is an open set in the standard topology on the real numbers. So we're talking about the standard topology on the real numbers, and let's look at this set first. Is this set closed? Yes, this set is closed. How do I know it's closed? Because its complement, what is the complement of this in R? The complement of this in R is 0, 1. Do you understand what this looks like? Is it hard for us to get that in our heads?
No.
Here's a real number line. Here's 0 on the real number line. Here's 1. This is starting at 0, all the numbers this way, and starting at 1, all the numbers this way. What are the only numbers we didn't use? The numbers between 0 and 1, 1, that open interval. That's all we didn't use. So the complement of this is this. The complement of this is this. Is this open? Wonderful. Then this is closed. Make sense?
Okay.
Let's look at another one. The closed interval A to B. Is that a closed set? Better be. This is where it gets its name. So, we've got R. There's R. We've got A somewhere on here. And we've got B somewhere on here. And we're talking about the complement of this. So we've got A, we've got B, we include them. What's the complement of that?
Everything else.
It's negative infinity to A, not including A, unioned with, not including B to infinity. Open interval, union of open intervals
Okay.
is an open interval. So yes, the closed interval, hence closed AB, is a closed set in the standard topology. Good? Alright, let's look at the last one. We said the set gets 6. Now here's a trick one. 6, just that point. Is that closed?
Yeah.
Is it?
Yeah.
So you're telling me that negative infinity to 6, union with 6 to infinity is open?
Sure.
Because you're not including.
Yep,
six.
sure makes sense to me. Everything but 6, yep, that's open. Therefore 6 is closed.
Yes.
Let's try another one. On the shared topology. Is that closed?
Yeah.
Standard topology on R, is this closed?
Yeah.
What's its complement?
The empty set.
The empty set. Is this open?
Yes.
Then this is closed. Is this open?
Yes.
Then this is closed. They're complements of each other. So R is open and closed. The empty set is open and closed on the shared topology on R. Right?
Yeah.
Okay.
R is closed. Why? Because R complement equal to the empty set is open. And the empty set is closed. Why? Because the empty set complement, which is equal to R, is open. What does it mean to be closed? It means your complement is open. That's it. That's all it means. Good?
Okay.
Okay, you said it. So we did that example. Okay, next definition. Now, before we go over this definition, let's remind us of definitions we already know. We talked about an open ball already, right? What was an open ball? It was I pick some point X, I pick some radius R, then the open ball was all the points whose distance is less than R away from X, right?
Yeah.
We're going to define a closed ball now. The only difference is we include the border. And so to signify a closed ball, we put a line above the B. So let's just see. So let X be any point in R2 and let R be any positive number. Then the set B with a line above it, that line above it's very important, X comma R, is equal to the set of all points in R2 whose distance is less than or equal to R. Closed ball. A ball that includes its border. And it's called closed ball. Straightforward definition?
Mm-hmm.
Similarly, we already had the concept of an open rectangle. You remember what that was? We take any open interval on the x-axis, AB. We take any open interval on the y-axis, CD. And we take their Cartesian product. So we take this open interval and we cross it with this open interval. And it gave us this open rectangle, which didn't include its boundary. Right? That's called an open rectangle. When we include its boundary, it's called a closed rectangle. How do we include its boundary? Instead of using open intervals here, we just use closed intervals here. If you cross two closed intervals, you get a closed rectangle, which is exactly what our definition is. The set AB crossed with CD, where these are closed intervals, is called a closed rectangle. Oh, that was just pictures from before explained. Straightforward definitions?
Yeah.
Think you got it? Okay. So now we're going to prove that a closed ball is closed in the standard topology. Right?
Okay.
So that's what we're going to do first. So let BX, let the closed ball, or let this be a closed ball. Let's see. And I'm trying to prove that this set is closed. What does it mean to be closed?
Its complement
Its
is open.
complement is open.
So let's name its complement real quick. So let this be a closed ball, comma, and let, I'll call it U, equal its complement. So I need to show that its complement, U, is open. Right?
Okay.
Now let's draw a picture of what we're doing here real quick. So I've got, here's X, and I've got some radius R, and I've got the closed ball. Now its complement is everything out here, not including the boundary.
Okay.
So if I were drawing its complement, the way I might have drawn it is like this. Dot, 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 dot. And said it's all the points out here, right? Not including that circle.
Okay.
So we're proving that this outer set is open. That's what we're trying to do. How do we prove that a set is open in the standard topology?
That it's
Show that it's
a union of other open sets.
It's a union of open balls is the standard way to do it, right? So let me erase my picture here and restart one more time. So here's X, here's R, here's our closed ball. I'm trying to prove that this is closed, which means that I need to prove that everything that's not this ball is an open set. How do we show that something, what does it mean to be an open set in the standard topology in R2? It means you're a union of open balls, right?
Yeah.
Okay.
So, I'm going to take some arbitrary point out here, y, and I'm going to show that for any y out here you pick, I can construct an open ball around y such that this open ball be, we'll call it y epsilon. What am I doing? My hands, why did you do things? I'll show that for any y here, I can construct an open ball at that y such that this open ball is a subset of u being the complement of this thing. Right? Remember how I defined u up here. U is everything not in that circle, so use everything out here. Let me show you for any point in u you grab, call it y. I can construct an open ball around y with some radius epsilon such that this open ball is a subset of u. If I can do that for every point in u, construct one of these open balls, then the union of all those open balls is u.
Right.
Union lemma.
Right.
And since u is a union of open balls, u is open. And since u is open, its complement is closed.
Yeah.
That's big picture what we're going to do. Follow all that?
Yeah.
All right, so let's actually do it. So let this be a closed ball and let u be its complement. So we need to grab some random point in here, let y in u, comma, and now we need to construct an open ball around it. So I need to come up with an epsilon for that y. And let epsilon, we want it to be a positive number because it's going to be a radius. Let epsilon be a positive number such that, what do I want epsilon to be? I want it to be less than the distance from x to y minus r. Here's the distance from x to y, right? R gets me this far. So as long as my epsilon is less than this distance, we're good, right?
Mm-hmm.
That will keep my ball completely outside of this circle. Okay, so let y be some point in there and let da 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 da. 3. It remains to show, we'll just note it here, even though I think you're all following fine. It remains to show that the ball at y with that radius is a subset of u. Okay? Once we've done that, we're done. So I'm going to prove this by way of contradiction. What I'm going to contradict here is the triangle inequality. So let's remember our intuition for the triangle inequality. What does the triangle inequality say?
The sum of two sides is always greater than that third
That's
side.
right.
Greater than or equal to, because we allow the case where all 3 points are all on the same line.
But that's not.
I know it's not, but if you think about it in terms of discrete math, or not discrete math, in real analysis, we're just talking about absolute values. It's just thinking about in triangles is most intuitive for not going to absolute values because I can't go over all the theorems for absolute values from real analysis.
Okay.
So we allow all 3 points to be on a line, but what it says is pick any 3 points in R2. Doesn't matter. Then the distance going from one point then to the next is always less than or equal to the distance going just straight to that point. In other words, the shortest distance between 2 points is a straight line, is one way you might intuitively think about it. Make sense? So I'm going to get a contradiction here. I'm going to find a shorter path by going like this, and it's going to be shorter than this path, which is an obvious contradiction.
Okay.
That's the contradiction I'm going to get. Okay, so let's get our contradiction. It remains to show that this is a subset of u. So let z in that ball be y epsilon, comma, and assume by way of contradiction, that z is in the closed ball. So I'm going to show that Z can't be in the closed ball, therefore Z is in U, therefore every point in here is in U, not in the closed ball.
Okay.
So Z is just some point in here. I'm saying assume by way of contradiction it's possible for Z to also somehow be in here. Since Z can't be in here, Z has to be in U, therefore every point in here is also in U, therefore this is a subset of U, therefore by the union lemma, U is equal to the union of all these things, therefore U is open. Follow that?
Yeah.
Okay. So, 5. Then, the distance from X to Z plus the distance from Z to Y is less than. Remember, if Z is somehow in this ball, then the distance from X to Z is less than R. And if Z is in this ball, then the distance from Z to Y is less than epsilon. So this distance plus this distance has to be less than R plus epsilon, right?
Yeah.
But by definition, epsilon is less than what?
The distance from X to...
The distance from X to Y minus R. So the distance from X to Z plus the distance from Z to Y is less than R plus epsilon. But epsilon is less than the distance from X to Y minus R. So making that substitution, this is now true, which is equal to the distance from X to Y. Contradiction. Right? Because I just barely got the distance from X to Z plus the distance from Z to Y is less than the distance from X to Y. Contradicting the triangle inequality. That can't be true. The distance from here to here plus the distance from here to here cannot be less than the distance from here to here.
Yep.
Okay. Therefore, Z is not in the closed ball, which gives that Z is in its complement U, which gives that the open ball is a subset of U, right?
Yep.
And then we can do this for every point Y in U. So then U is equal to the union for all Y in U of those open balls that we can create at Y with some radius epsilon. We find epsilon for each Y that we pick out in this way. So then U is equal to this. These are all open balls, which means U is in tau. Which means that U complement is closed. And we're done. Right? Any questions on that proof?
No, I think it was pretty straightforward.
Pretty straightforward. The proof that the book does is that closed rectangles are closed. They don't prove that closed balls are closed, but the proof's very similar.
Okay.
So, how would I prove that a closed rectangle is closed? Well, a closed rectangle, what's its complement? It's everything not in that rectangle, right? So I'm going to draw its complement on the board. Its complement is this set, right? Everything out here. But notice that that is the union of this half plane with this half plane with this half plane with this half plane, which are all open sets. So it's a union of open sets, so it's open, so its complement, which is this closed rectangle, is closed.
Gotcha.
There's a quick intuitive way to see it.
We just called the top plane a half plane and the bottom plane the half plane. And then there's a space in between them.
Yes. Two halves do not make a whole.
Apparently they don't.
Just a name once again, the half plane. Okay.
Can you have an open set within a closed set?
Sure.
Can you show an example of that?
Take any closed set in R2 that you want. We'll take the closed ball.
Okay.
That contains the open set, namely the open ball. Get rid of the border, you now have an open set. So the open ball is a subset of that. Or, of course, here's one. Any weird open shape that you make there that doesn't include its border is also an open set. Contains infinitely many open sets. Any other questions? Okay, and let's do some intuition examples. Look at all these sets. Which of them are open and which of them are, sorry, not open. Which of them are closed in R2 is what we're going to ask.
Okay.
So I've got this plus symbol, the intersection of two line segments. Is this closed?
Yeah.
Yes.
What?
Is this set closed? It's the intersection of two line segments.
Why would that be closed?
Because its complement is open. So let's look at its complement. Its complement is everything except for these points and these points, right?
Yeah.
You see it now?
Yeah.
Okay. What about this one? Is this closed?
Yep.
Sure? Is it not appealing to your intuition?
Yeah, it is. I see it.
Okay. That's all that we're not rigorously proving any of these. We're just trying to help establish your intuition for what is open and closed in the standard topology on R2. What about this one? Is this closed?
No.
Yeah.
Yeah.
Yeah, we got a yeah and a no. Let's draw its complement real quick. What does the complement of this thing look like? We've got a closed circle here, all the points in there, and then we've got open here, and then we have all the points out here, right?
Okay.
Is that open? No! How can I union up open balls and get this closed border?
Okay, wait. What? How is that closed?
Okay, that makes sense.
This, it's not closed. That's what we're saying. This is not closed because this is not open. This is its complement, right? Are my pictures throwing you off? The book is bare pictures.
Okay, I see what you're saying.
Yeah,
Now that makes sense.
it makes sense now.
Good? Okay. Finally, this one, is this closed?
No.
No.
Depends on what your universe is. If you're
In the standard topology on R.
Okay.
Yeah, these were all just for the standard topology on R to give you intuition for that one because that's the common one used. Like when you do two-dimensional calculus, we talk about standard topology on R2. Good?
Okay.
All right. So just some examples to help establish intuition. Don't move until I change my camera. Let's see if we can get the rest of the whiteboard. Okay. Blackboard, chalkboard, not whiteboard. All right. So finish that. Now let's see. Oh, more examples. So let X be some set with the discrete topology. You remember what the discrete topology is?
Isn't it just...
Powerless set?
The power set of X. It's the set of all possible subsets of X.
Okay.
So what are the open sets? Any possible subset of X you can think of. That's an open set. Okay?
Okay.
What are the closed sets in that topology?
Wouldn't it be the empty set?
Also any of them?
The empty set, that is closed. Why? Because its complement, all of X, is a subset of X.
Yeah.
So yeah, that one works. Is that the only one?
No. X would. All of X would.
All of X would be closed. Why? Because the empty set, its complement, is a subset of X.
Wouldn't every single subset?
Yeah, wouldn't it?
Every single subset of X is closed because the complement of a subset is still just a subset. And every single subset's open. Therefore, every single subset's closed.
Okay.
You take the complement of a subset, what do you get? You get a subset. Right? You can't take the complement of a set and end up with more than the set you're taking more than X, right? Okay. So does it make sense that What are all the closed sets? The power set of X. Those are all the closed sets. Same as all the open sets. Every single set is open and closed. Every single subset of X is both open and closed in that topology. Make sense?
Yep.
Alright, let's do a more discrete example to try and make sure we're getting this intuition. So let X be the set A, B, C, D. Here's the topology we're going to give it. The empty set, the set containing B, the set containing AB, the set containing CD, the set containing BCD, and X. First off, is acting a topology.
Yeah.
Is the empty set in there?
Yeah.
Is X in there?
Yes.
If I take the intersection of any finite number of things in there, do I get something in there?
Yeah.
Yeah.
If I take the union of any finite number of things in there, do I get something in there?
Yeah.
What about the union of AB with CD?
Oh no.
See, we're missing one, right?
Yeah.
No, we're not. That's X.
Oh,
Right. Okay.
wait, where's? Oh, never mind.
So are we convinced this is topology? And we're not just saying that because you know I went write something up there that's not topology, but you've actually thought about it. Yes, that's topology. Makes sense.
Okay.
Okay, now I want you to tell me all the closed sets. What's the first closed set?
X.
That's the second one. What's the first one?
Yeah, just said.
I'm just kidding. X, yes, that is one. All right, what's another one?
Yeah.
The empty set. Okay, we're doing these in a weird order now. What else?
ACD.
ACD, the set containing ACD.
Mm-hmm.
Okay.
CD.
CD, but that one's open.
So.
So, good answer. What else?
AB.
AB.
And A.
And the set containing A.
Mm-hmm.
Good. There's all our closed sets. Any questions about that? Discrete example help?
Yeah, it helps.
Okay. We're going to kind of move forward away from examples, I think, for now. So, do you feel like you're good with open sets versus closed sets, or do you want to see more examples of a particular type before we move on?
I think we're good.
Think you're good? Okay. So, moving on. Notice that a lot of the times that we're trying to prove that a set is closed, it's showing that its complement is open. That's how we show a set's closed. We prove its complement is open. So we're often dealing with the complements of sets when we're trying to do proofs with closed sets. And so there's a very useful theorem that we've already shown in this class, but we'll go over it again because it's very important when dealing with closed sets. And it's just De Morgan's, for those of you that remember what De Morgan's is, with sets. So, what does it say? It says that if you have A intersect B and you take its complement, that's the same thing as A complement union B complement. And if you take the complement of the union of two sets, then that's A complement intersect B complement. So this is De Morgan's with sets. Do you guys remember what De Morgan's is in general?
I think so.
What?
It's just like the opposite.
No, it's this. De Morgan's right here. Not A or B is not A and not B. And not A and B is not A or not B.
Yeah.
Okay, yeah, that's De Morgan's. And so you can see how using De Morgan's here is the exact same thing. If it's not A and B, then it's not A or not B. Similarly, if it's not A or B, then it's not A and not B. Same exact thinking. But we'll write it out. Here's what we proved earlier in the class. It doesn't quite look like this, but it's the same thing. We showed that X minus A union B is the same thing as X minus A intersect X minus B. You might remember that from chapter 0. But notice what is X minus A union B?
It's S.
When A and B are subsets of X, is just that. This is the complement of A union B.
Yep.
Similarly, when A and B are subsets of X, then this turns into this. Make sense?
Mm-hmm.
Same thing, we prove this one down here, gives us the exact same result. And then in case we need an explanation, I did the proof here. You want to go through the proof or you think you got it?
Can we go through the proof?
Yeah, we sure can. Okay, so this being true is just a result of De Morgan's, going back to basic propositional logic. So observe that not A or B is the same thing as not A and not B, right?
Mm-hmm.
If you're not at home or at school, then you're not at home and you're not at school. Right? Similarly, if you're not 10 feet tall and a girl, then either you're not 10 feet tall or you're not a girl. Right?
Mm-hmm.
You might not be, right? Both those might be false for you, but at least one of them has to be false. Or, so the intuition for De Morgan's back to basic propositional logic makes sense?
Yeah.
Or do we need to try and make that appeal to your intuition more?
That's
Good?
Yeah.
Okay. So, now let's write out what we meant with union and intersection. It's not the way we defined it in this class, but back in discrete math, what do we mean by A union B? It's everything that's in A or in B. We defined it in propositional logic that way, so think about it that way. So observe that if X is in A union B, that's identical with X is in A or X is in B, right? Similarly, X is in A intersect B is the same thing as X is in A and X is in B. Good? Okay. So then, if X is in the complement of A union B, that's the same thing as X is not in A union B, right?
Yeah.
And if X is not in A union B, that means X is not in A and X is not in B. There's where we're using De Morgan's a little behind the scenes, right?
Yeah.
If it's not in this or this, and it's not in this, and it's not in this.
Mm-hmm.
I didn't want to write out the full set definitions. I thought you could make that leap, right?
Yep.
Yeah.
Okay? And then, if X is not in A, that's the same thing as X is in A complement. And X is not in B, that's the same thing as X is in B complement. And then, if X is in A complement and X is in B complement, that's the same thing as X is in A complement intersect B complement. Right?
Mm-hmm.
So I just barely showed X being in this is logically equivalent to X being in this. So they're equal. Follow that? And then almost identical thinking for this one. X being in A intersect B complement, that's the same thing as X is not in A intersect B, right? And if X is not in A and B, then X is not in A or X is not in B. That's De Morgan's behind the scene. And X is not in A or X is not in B is the same thing as X is in A complement or X is in B complement. And then that's X is in A complement union B complement. So this is logically the same as this, so those two are equal.
Okay.
Make sense?
Yeah.
Now we'll see why this is so useful for our next proof. Oh. I don't know if I need to stress it more. I didn't know how much I was going to have to stress this, so I read with a picture example of them too. You think we're good? Or you want the pictures?
Explain the pictures.
I like
Yeah,
pictures.
explain.
You like the pictures? Let's do the pictures. So I'm just going to color in those sets. And we'll see that they're the exact same thing. So what is A intersect B complement? That's the complement of A intersect B. So that's everything out here, everything here, and everything here, right?
Yeah.
Everything except for A intersect B. It's A intersect B's complement, right?
Okay.
Okay.
Follow that?
Yeah.
Okay. Now, let's play again. I probably should have just done this one and shown it as the same as that, because that one's easy to see. But let's play the game again, and now let's look at this one. So we're doing A complement union B complement. So A complement is everything that's not in A, right?
Mm-hmm.
So that's everything out here once again, and everything over here. That's everything not in A, union with everything not in B. Well, once again, that's everything out here and everything in here. What did we leave behind? Just A intersect B.
Okay.
Good?
Yeah.
Okay.
So maybe this one, I'll start with the bottom one and show it's the same as the top. So let's understand what the top one is. A union B complement, that's just everything out here, right?
Yeah.
Yeah.
Okay, so now let's look at this one. We look at A complement, that's everything not in A,
Okay.
and we intersect it with B complement, everything that's not in B.
That's just the outside.
And that only leaves the outside. You see it?
Yep.
Yeah.
Okay, here's our pictures. Any questions about that before I move the camera to the whiteboard? All right. Let's see. Perfect. Okay. So now, this marker's kind of dying on me right at the end. We'll see how purple does. Now we'll prove some interesting properties that closed sets always satisfy. And pay attention to how this corresponds with open sets. So let X be a topological space, then it's always going to be the case that the empty set and the entire set X are closed.
Yeah.
Notice over there that those sets are also required to be open.
Mm-hmm.
Secondly, if you have a finite number of closed sets, then their union is closed. Over there, we said if you have a finite number of open sets, then their intersection is closed. Here we're saying if you have a finite number of closed sets, then their union is closed. Over there, we said if you have an arbitrary collection of open sets, their union is open. Here we're saying if you have some arbitrary collection of closed sets, then their intersection is closed.
Okay.
Very similar.
But that bottom one is union, and this one is intersection.
Right, depending on which order you want to do it. I could have flipped the order so that they're talking about union and intersection, and then it would have been this one was arbitrary versus this one was finite.
Right.
However you want to think about it. Yeah. Good? Okay, so this is what we're going to prove. I'm just going to prove this part, then this part, then this part. Obviously, the first part of this proof is real easy, right?
Well,
Oh,
yeah, you
yeah.
could say that the empty and X are
Right.
open, and they are complements.
Since X complement equal to the empty set is in tau, that gives us X is closed.
Mm-hmm.
2, since the empty set complement, which is equal to X, is in tau, that gives us that the empty set is closed. Okay, those were the easy ones, right?
Yeah.
Yeah.
Okay, now let's do proof of part 2. I don't know if we need separate lines. We'll just see here. Since I'm talking to you, it doesn't matter. Okay, so to prove part 2, what do I need? I need to assume that I have n closed sets, and then I need to prove that their union is closed. How am I going to prove that their union is closed?
Show that
They're showing that the
Yeah.
complement is
Complement is open. And so I'm going to be taking a complement of unions of sets, which is going to give me intersections of sets. And we know that intersections of finitely many open sets are open. We'll see it one step at a time. No reason to point it all out once. Okay, so 3. So let A1, comma, A2, comma, dot, 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 comma, AN be closed, and let U equal the union from I equals 1 to N of A sub I equal the complement of the union of all of them.
Okay.
U is a complement of all their unions. I'm trying to prove U is open, therefore their unions is closed. Their union is closed. Good?
Mm-hmm.
Okay. So, then, maybe I'll just name may want to call this thing closed, so we'll call it V. So we'll let V equal their union. I'm trying to show V is closed, so I need to show V complement is open. I just don't want to have to rename this thing. So then V complement, which is equal to the union from I equals 1 to n of A sub I complement, which is equal to the intersection from I equals 1 to n of A sub I complement. It brings the complement inside the parentheses and applies it to each of the sets.
Yeah,
You follow that piece?
No.
Oh,
just what we did over.
that's the hardest part of the proof. So over here we only proved it for a case where we had 2 sets, but this is true in general. For 3 sets, for 4 sets, you can prove this inductively real easy, because if I were to have 3 sets, intersect 2 of them together, now I only have 2 sets. It's true for 2 sets, so it's going to be true for 3 sets, etc.
Gotcha.
But, so what is this saying? Let's pretend that n is 3 for now, just so you can see it. But obviously this is true for any number. So the union from I equals 1 to 3,
That's fun.
3, my hand, okay, of A sub I is equal to A1 union A2 union A3, right?
Okay.
Now we were doing the complement of the whole thing, so then we're doing the complement of this whole thing. Well, that's equal to A1 complement intersect A2 complement intersect A3 complement. That's what we proved over here.
Yep.
Or another way to see it really intuitively is not A1 or A2 or A3 is the same thing as not A1 and not A2 and not A3. Right?
Yeah.
Okay.
If you think about where X can go in here or here or here. Not is the same thing as X cannot go here and X cannot go here and X cannot go here. Think about the individual elements in the set. That's kind of how I think about it, but whatever helps. So that's what we're doing, going from here to here. You follow that step?
No, dude.
Okay. But what do we know about A sub I complement?
They're all open.
It's open. How do we know it's open?
Oh, right, because it's the complement of the closed.
Because A is closed. All those A's are closed, so all their complements are open.
Therefore, the intersection is open.
So V complement is equal to that, which gives us V complement is open, which gives us that V is closed.
Oh, wait, well, it's faster than I thought it was.
Yeah.
That's why I wanted to name that thing V, so I didn't have to write it again. Follow that?
Yep.
Yeah.
Okay, now we're going to prove this next part, and this next part's proof is going to be almost identical. So 5, let A sub alpha be any collection of closed sets and we'll just use V again. Common notation I think that this author uses is U for open sets and V for closed sets. So
Okay.
we'll try and follow that convention. So let that be any collection of closed sets and let V equal their intersection. With me so far?
Mm-hmm.
Okay, 6. Then V complement is going to equal the intersection A sub alpha, whatever that intersection is, that thing's complement, which is equal to the union of all the individual complements, which is in tau, which gives me that V is closed. I think you can follow that, right?
Yep.
Anything weird there? Needs written out better? Feel like you understand it?
Yeah.
Any arbitrary collection of open sets unioned up is open. That's the third property of a topology, right?
Yeah.
Okay.
Good? So that takes care of that. Now we know that closed sets satisfy these three properties. Our next definition. A topological space X is called Hausdorff, provided that for any 2 points in there, Hausdorff, this guy's a mathematician that first listed out the basic properties that topology has. And this property that we're going to list right now, he thought was another property that they had to have. They were later reduced to just those three, not including this. And so now we talk about two topologies, topologies that Hausdorff talked about, and then topologies that are more general than the ones that he talked about. So that's why they're called Hausdorff. Now it turns out his name has a nice way of helping you remember what the property is. Everyone who's taken a topology class remembers what a Hausdorff topology is. And you'll see that here in a second. So it's convenient that his name is Hausdorff. Okay, a topological space X is Hausdorff provided that for any 2 points, I'm calling them points, we're not in R2, I'm just, any 2 members, any 2 elements in X, for any 2 elements in X that are not the same element, then there exist neighborhoods, or open sets containing them, neighborhoods of those points, such that their intersection is empty. Or in other words, if you have 2 different points in the topology, they have 2 disjoint neighborhoods. And why is Hausdorff so memorable? These points are housed off from each other. They have their own separate open sets, their own neighborhoods. So that's how most people remember it, is housed off. Any 2 points you pick, they're housed off. They have their own separate neighborhoods, their own separate open sets. Guaranteed. Good? Feel like you understand the property?
Yeah.
Okay, now let's just prove a bunch of things have this property, and we're done. Okay, first thing we want to prove. The standard topology on R is Hausdorff. So
What's
how...
the standard topology again?
Standard topology on R, it's all the...
On R, did I say R2? I meant R.
R.
The standard topology on R is the empty set, all open intervals, all union of open intervals.
Okay.
Those are all the open sets in the standard topology on R. Now we're going to prove that it's Hausdorff. How are we going to prove that? We need to show that anytime you pick 2 elements in R that aren't the same, we can find 2 neighborhoods containing those points that don't intersect. Make sense?
Yeah.
Yeah.
So, 1. Let x, y in R such that x is not equal to y. 2. Without loss of generality, comma, let x less than y. What do we mean by without loss of generality? We mean you could always call the smaller one of the 2 x and the bigger one y. So if you have to relabel them real quick, relabel them real quick.
Okay.
So we've got 2 points that aren't equal, then for sure one's less than the other. Call the smaller one x and the bigger one y. That's what we mean so far. Right?
Okay.
So let's draw a picture real quick. I think it's obvious what to do, but let's draw a picture to make sure it's obvious. So what do I need to do? I need to find an open interval around here and an open interval around here such that the 2 open intervals don't intersect. And I'm done.
Mm-hmm.
Right?
Yeah.
So what is the open interval around here and the open interval around here? Just say it in words, if you can.
Well, you would take the distance from x to y divided by 2. and
Take-
then-
Perfect.
Not including that.
So take half their distance and then create open intervals centered around them like that.
Right.
Yep, that's one easy way to do it. No reason not to do it that way. We won't do it the way I thought of. I'm just going to take the midpoint and then...
That's what.
Isn't that what we just did?
No, we took half the distance.
Okay.
So that, and I'll call it the epsilon, equal, what's half the distance?
The midpoint.
But what exactly is it? Tell me the equation.
It's the absolute.
The distance between the
We
2
don't need to do
divided by
absolute
2.
value because we know which one's bigger.
Oh, so it's y minus x divided by 2.
Y minus x over 2. So let epsilon equal y minus x over 2, right?
Okay.
Then x minus epsilon to x plus epsilon intersect y minus epsilon to y plus epsilon is equal to the empty set, right? Those are two disjoint open intervals.
Yes.
Okay.
We could write all that out with inequalities, but I think you know how to do that, right?
Yeah.
With inequalities.
Yes.
Right, that'd be real easy. So their intersection is the empty set, which gives us it is Hausdorff. Alright, we just readily found two separate neighborhoods containing those points that don't intersect. And that's all it means, is that there's at least two neighborhoods out there containing those points that don't intersect. There's tons of neighborhoods that do intersect, there's tons that don't, we just need to find two that don't intersect.
Only two.
Only two.
Whole thing.
There can be more, at least two.
Okay.
There's at least two open sets I can find containing those points such that they don't intersect. Make sense?
Yep.
Are you able to give an example of a topology that isn't Hausdorff?
It's such a natural property, there's a reason that he thought it would just come up, that it's very hard to come up with intuitive natural topologies that don't have this property.
I see.
So all the ones that we're going to list here real quick, we're just going to go over some basic ones that are talked about in the book, all are going to have this property. So it's very natural that topologies have this property, which is why he thought that topologies would always have it. But it turns out there are topologies that don't. Okay, next, let's do another one. If X is a Hausdorff space, this is a little bit different one, our last theorem. That was just an example, and then these are two more proven that they're Hausdorff. Okay, if X is a Hausdorff space, then the singleton set is always closed. If X is Hausdorff space, then for every little x and big X, the set just containing that point is closed. Right? We just showed that the real numbers are Hausdorff. What does that mean? That means in the standard topology, the set containing 6 is closed.
Okay.
Right? The set containing just pi is closed. The set containing just put any real number you want in there is closed. We're going to show that if you know that a topology is Hausdorff, then you know that this is the case. Anything weird about that, what I'm saying? Just waiting for me to do it? Okay. Okay, so that's what we need to prove. If we're going to prove that it's closed, we need to show that its complement is open. So, let little x in big X, comma, and let u equal x minus little x. Everything that's not that point. Two. That was the best way to say this. What do I know about x? I know it's Hausdorff, right? So I know that anytime I have 2 points that aren't the same, maybe grab a point in here real quick. Maybe big picture, how am I going to do this? How am I going to do this? I'm going to do this the same way that we prove every set is open. I'm going to grab a random y in U. I'm going to show that I can find an open set containing y. And since I can do that for every point y in U, then by the union limit, let me say it again. I'm going to grab some arbitrary y in U. I'm going to show that I can find an open set that contains y that's also a subset of U for any y you pick. Therefore, the union of all those open sets is going to give me U by the union lemma. U is a union of open sets. Therefore, U is open. That's big picture how I'm going to go with this, right? So the only trick is once I pick a y in U, I need to find now some open set that's a subset of U that contains y. That's the whole trick to the problem, right? With problems like these.
Okay.
So if I'm going to find a set, an open set that contains y that's in U, what's the one thing we know about that open set? If the open set is a subset of U, what's the one thing we know about it?
It's open. If that open set is.
What's U?
U.
Tell me what U is in words.
It's open.
It's, how would you describe this set?
U is its complement.
It's the complement of little x. What if someone didn't know what complement meant? How would you tell them what this set is?
It's everything.
It's everything except
Little.
little x. This is everything except little x. So any subset of this can have everything except
X.
little x.
Yeah.
So all we need to require is that our whatever subset we have that contains y doesn't contain little x.
Okay.
So I need to find a set that contains y that doesn't contain little x, and it will be a subset of u.
Okay.
Is there going to be an open set that contains y that doesn't contain little x?
Yeah.
Yeah.
How do I know that?
The
It's
set just
open
containing
ball.
little y.
Because it's Hausdorff. For any 2 points I pick that aren't the same point, notice it's y is in u, it's definitely not x. For any 2 points I can find that aren't the same point, I can find disjoint open sets containing them, which means I can find an open set around y that doesn't contain x.
Oh.
You see it?
Yeah.
Okay. So let y in u, and note that since big X is Hausdorff, then there must exist two open sets. We'll call them u sub y and v sub y, such that, we don't really care about this v sub y, but it tells us that they're there. There exist two open sets u sub y and v sub y such that x is in u, or not x, y is in u sub y, x is in v sub y, and u sub y intersect v sub y is equal to the empty set.
Why are you calling the neighborhood around x v sub y?
And it doesn't matter what we call it. I just need to give it a name and say that there is a different one for every y that we pick. So it doesn't matter what we call it here. I just need it for each y. So if you don't like v, since we use that for closed sets, we can just call it an a.
Wouldn't you call it v sub x? Since it's the neighborhood around x?
No, because x doesn't change. Our y changes for each y we pick in u. So let's draw a picture of what we did real quick. So here's our x, and use everything that's not x. So x stays fixed throughout this whole proof. Then we say, pick any y you want. So when you pick this y, here's your u sub y, and here is your, what did I call it now? A sub y. Now pick this y. Now here is your u sub y, and now your a sub y has to change. It needs to be something that doesn't include any of these, so now a sub y might be this thing. So with every y, it changes.
Okay.
Okay.
So that's why I can't use the subscript, this x, because this x stays fixed throughout the whole problem. This y, we're showing how to do it for one y, then you can do it for every y.
Oh, I see.
Because we're going to use ultimately the union lemma, right? Okay, so maybe you have our picture over here to help us keep track of it. Here's x. Use everything that's not x. We said, let y be anything in u. Okay, there's a y. And we said that since x is Hausdorff, there must exist neighborhoods. Here's u sub y. and here's A sub y, there must exist two neighborhoods, these are just names, such that their intersection is empty, right?
Mm-hmm.
Then, maybe since x is not in u sub y, then u sub y is a subset of u. Right? What was u? U is everything that's not x. Since x isn't in this u sub y, then this u sub y is a subset of u. Does that make sense?
Yes.
Good? Okay. So since x is not in u sub y, then u sub y is a subset of u. 4. Then u is equal to the union for all y in u of u sub y. Right? We just barely showed that for any y you pick in u, we can create a neighborhood around it, we can create an open set around it, such that that open set is a subset of u. So then by the union lemma, u is the union of all those points, or of all those sets. We create one for each little y in u. And that gives us that u is open, because it's a union of open sets, which gives us that u complement, or x, singleton x, is closed. And we're done. Anything weird?
I do have a question.
Yep.
So why couldn't we have just shown that for any y you chose, there's an open ball around y that doesn't contain x?
So we're not in any particular topology, so we don't have open balls.
Right.
We need an open set around it that doesn't contain x.
Okay.
How do I know that u sub y doesn't contain x?
Because it's Hausdorff.
Because x has to be in this other set, and these two sets are disjoint. So I didn't really care about this set. I'm just using this set real quick for the fact that, hey, x is not in there.
Right.
Any other questions? Good? All right. So, 2 more problems that were just homework problems that I chose, and then we'll be done. So that was everything for new material. These were just examples to help us get comfortable with showing things are Hausdorff. Okay, next proof. Prove that the lower limit topology on R is Hausdorff. I don't think we've gone over the lower limit topology. The lower limit topology is when your basis is intervals like this. Include the bottom, don't include the top. Okay. Right? The standard topology was open intervals. The lower limit topology, we include the bottom point, we don't include the top point. Now notice in this topology, every set that's open is also closed. You see that?
No.
Let's see. Give me one that's open real quick, a particular set.
3 to 5.
3 to 5 like that is open, right?
Okay.
Let's look at its complement. What's its complement? Its complement is negative infinity to 3 union with 5 to infinity. This is open. This is open. So this is open. So this is closed.
Okay.
Okay? Lower limit topology, any set that's open is also closed.
How is negative infinity to 3 open?
Could I create this from a union of these things?
Yeah. Okay.
All right. So that's the lower limit topology. Now we need to prove that it is Hausdorff. It's going to be very similar to this one, probably identical, I don't know. So let x, y in R such that x is not equal to y. 2, without loss of generality, let x be the smaller of the two. Okay? Now I just need to come up with intervals or open sets containing those two things that are disjoint. Right? Let's draw the picture real quick. What do we have? We have x here, we have y here. I need to come up with two intervals containing those things. Two intervals like this containing those things that are disjoint. And we're done. Right? So 3, let m equal the midpoint of those two, x plus y over 2. What am I going to do this time? So here's m, it's the midpoint of those. All I'm going to do is take the interval x minus 1 to m and m to y plus 1. Those are my neighborhoods.
Okay.
Right?
Yep.
In fact, I probably don't even need to finish. You see how it goes. That's it. This, by the way, is how I was going to do this one.
Yeah.
Okay, so that one was easy. Let's see if this one's harder. The finite complement topology on R is Hausdorff. Okay, do we remember what the finite complement topology is? A set is open in this topology if its complement is finite.
We went over this before?
Yep. One of the first topologies we went over.
Oh, that makes sense.
I think it might have been the very first example of a topology on R that we went over.
Okay.
So let's look at an example of something that's open on this. 0 to 3 is open, right?
Yeah.
No, not by a mile. What's the complement of this thing?
A lot of numbers.
Negative infinity, not negative
Oh,
8.
The finite complement.
Negative infinity to 0, union, 0 included, union 3 to infinity. Is this set finite?
No.
No.
No, so this set is not open. A set is open if and only if its complement is finite. What about this? Is this open?
Yeah.
What's its complement? The empty set. Is the empty set finite?
Yeah.
Yeah, it's got 0 things in there. That's pretty finite. Let's look at another one. What about that thing?
Yeah.
What's its complement?
2 and 9.
It doesn't have 2 and it doesn't have 9. It's everything but 2 and 9. Is that finite?
Yep.
Yes. So this is open. This is open because its complement is finite.
Doesn't have everything between 2 and 9.
It has everything from negative infinity to 2, and everything from 2 to 9, and everything from 9 to infinity. The only thing it's missing is 2 and 9. Another way that we thought about the finite complement topology is start out with the real numbers. Now make a bunch of holes. Randomly pick holes. Get rid of that, get rid of that, get rid of that, get rid of that, get rid of that. That is an open set. What did we get rid of? Well, obviously we got rid of negative pi there. We got rid of 0. We got rid of 13. We got rid of 21. And we got rid of 27.2. Right?
Okay.
So its complement are these numbers. That's finite. Therefore, this set is open in the finite complement topology. Feel like you're understanding it?
Yeah.
Finite complement topology. Okay. The finite complement topology. Oh, we're proving that it is Hausdorff. Okay. So, let's see. 1. Let x, y in R such that x is not equal to y. What do we need to find?
Two neighborhoods that don't intersect around them.
2 neighborhoods that do not intersect around them.
I remember that really wrong. There's a neighborhood for each.
The finite complement topology on R is Hausdorff. Yeah. So we need to find an open set that contains X that doesn't contain anything in Y. Let me think about this for a second. Is that right? The finite complement topology on R is Hausdorff. Or is it not Hausdorff? That seems weird. This is not Hausdorff. Okay. I was going to say, this isn't true. This is not Hausdorff. Okay. Huh?
Then we're just finding an example that makes it not. So
If you can find a counterexample, that works. But that's a real hard thing to do, because what do you need to do to find a counterexample? You need to find 2 particular points and say, see any neighborhoods you contain around this point and this point? Have an intersection? How do you prove that for infinite things? So this one's actually going to be easier by contradiction, I think. So, 1. Assume by way of contradiction that we don't have a name for it, so we'll just say that it refers to whatever this topology is. Let's give it a name. The finite complement topology tau on R is not Hausdorff. Assume by way of contradiction that tau is Hausdorff, comma, and let x, y in R such that x is not equal to y. Right?
Mm-hmm.
So, 2, then there must exist u sub x and u sub y in tau such that u sub x intersect u sub y is equal to the empty set. How are we going to do this? Similar way of contradiction. What is our contradiction going to be? Oh, we know that the complements of these things, whatever they are finite, right?
Mm-hmm.
So, let's see. Still don't know how I'm going to get my contradiction. Then there exists ux, uy, and tau such that their intersection is empty. Then I guess we could name their complements. Let Vx equal Ux complement and Vy equal Uy complement. So Vx and Vy have to be finite. Let's see, I know that. Oh, that's how we'll get it. I see now. So I know that the intersection of these 2 sets is the empty set, right?
Mm-hmm.
Which means the complement of this intersection has to be the complement of this.
But the complement of that
The complement of this is going to give me the union of two finite sets. The complement of this is going to give me R. Can I union up finite sets and get R?
No.
Union up two finite sets and get R? There's my contradiction. So let Vx equal this, Vy equal this. For since Ux intersect Uy is equal to the empty set, that gives us that Ux intersect Uy's complement is equal to R, right?
Mm-hmm.
You follow that so far? Which gives us that Vx union Vy is equal to R, which is our contradiction. Maybe we're not done yet. But I can't union two sets and get an infinite set.
Yeah.
So that's contradiction since Vx, Vy are both finite and R is infinite.
Wouldn't another contradiction be just like it equals R and R can't be a finite set? Like, isn't that your contradiction?
You're saying this.
Yeah, when you equal to R.
How do I know that this set over here is finite?
Because of the finite complement topology.
This is the step that tells me it.
Oh, okay.
Well, isn't also the intersection of two open sets open? So the complement would also be finite.
Oh, that's a great way to also think about it. You see what she's saying? The
No.
fact that we're keeping track of two sets here is just kind of making a mess for us. An open set intersection with an open set is
Open.
open. So you have an open set, but its complement is R. Contradiction.
Okay.
Because our open sets have a finite complement. And we just found an open set whose complement was R. No, it doesn't work. So yeah, you could have thought about it that way. That works too. Good? Any other questions? Alright, that does it for closed sets. And that does it for chapter 1. I guess you're the only one with the book. All the sections on applications, we're not going to bother with. They're really, while they're fun and interesting, they're kind of, I want to just say stupid, but I can't find a better word to use. Because it's so contrived, and it's like you're not actually seeing how it's actually applied. They just like walk you through the steps of, see, this is how they set up, and they do cool things with it. Because obviously you can't start doing cool things with it because you don't even know topology. So it's like, they put your foot in the door to say, and we do cool things, but that's it. It's like, thanks for that.